And then we have done this AC, we have done this EM waves, right? And then we have done this ray optics, and we are also doing this wave optics. These are the things that we have done. And what are the remaining chapters? So electric potential, that is remaining. Then we have this electric current. Then this is magnetics, which is very important. And then we have magnetism and earth. So earth magnetism, right? And fifth one is EM. So these things we have to complete here, right? We have to complete these chapters, right? Because yeah, what is the meaning? We have done that AC and EM. So that part. Okay, so yeah, we need to buckle up and do these things. Okay, so we were talking about electric flux, right? And we were talking about continuous systems, right? So we were talking about continuous charge. So first was this linear charge, right? And what was the idea? That the charges were, so the charges were placed on this line, right? So then what do we calculate? Then we calculate linear charge density. And for a uniform linear charge density, this remains in everywhere, right? So this was lambda, and this was defined as Q by length L, right? And if we take a small length L, if we take a small length dl or dx, right? And for that, the charge is dq. dq charge is there. So this lambda would be dq by dx, right? So we can also define this linear charge density like, right? Arsana, this is thing is
Yes,
clear.
sir.
Similarly, take we can talk about surface charge density. So surface charge density is defined as that we have these charges which are placed on the surface. Right. So example is this infinite sheet. Right. If I write it like this, so this is infinite sheet. Maybe this can be positive or this can be negative. Right. So this is infinite sheet. And for this sheet, we calculate the surface charge density. And this is represented by sigma, and this is Q by A. That is how we represent it. Okay. Similarly, we have this volume charge density. So we have this volume charge density, and this is equal to how much? So this is represented by rho, and this is Q by V. So these are the different kinds of charge density that we have. if we have a continuous type of charge density, right? So for the continuous charge density, I talked about three cases. One was this infinite linear charge density that we talked about. And then we talked about the infinite sheet. And we also talked about this. So then we talked about this hollow sphere. So we will try to calculate the electric field of these things using the Gauss law. So applying the Gauss law, we will try to calculate the electric field of this systems. Okay. So first, let us take an infinite linear charge. So we have this linear charge, right? And this is infinite. And we want to calculate the electric field of this thing, right? And let's say we want to calculate the electric field at this point. So what we will do is that we will make a Gaussian surface, right? We will make a Gaussian surface in such a way that the electric field is perpendicular to the area or electric field is parallel to these are the cases, right? That was the idea of the Gaussian surface, right, Asla? Do you remember?
Yes, sir.
Because we know that Gauss law is what? Gauss law is closed integral surface E dot ds. This was Q enclosed by epsilon. This was the Gauss law, right? And I discussed with you that we take the Gaussian surface in such a way that this thing and this thing are either perpendicular or parallel. So if they are perpendicular, then ADS cos theta is cos 90, so that is cancelled. Or if they are parallel, then ADS is parallel. So this is 0 degree, then this becomes simply E degrees. That was the idea of Gaussian series, right? So for that purpose, we will take a Gaussian surface which is cylindrical. So we will take a Gaussian surface which is cylindrical, right? So how many surfaces this cylinder has? How many surfaces? Yes. How many surfaces this cylinder has?
Sir, three.
Three, right?
The upper, lower, and the middle
And
part.
this curved one. Yeah, absolutely correct. Good. So there are three surfaces, right? So and these for these positive charges, the electric field lines are going in this direction, right? So they are coming out normally through this curved surface, right? Through this part is normally I'm talking about the upward and outward and downward, right? Because this is a cylinder. So let's say this is a line wire. So the electric field lines are going in these cylinders, right? In all directions, coming out in all directions. So if we have a cylinder, So electric field lines are going parallel to this, right? Coming out normally to this. Is that thing clear? So electric field lines are coming out like this. Electric field lines are coming out like this, right? They are coming out like so. They are coming out normally to the curved surface. Is that clear? That's enough.
Yes, sir.
Okay. So electric field lines are coming out like right? So on this curved surface. And as we have seen, we have three surfaces. So let's name them. Let's see that this is first surface. This curved one is second, and this is the third one. So if we apply the Gaussian surface, right? So if we apply the Gaussian surface, and if we calculate, yeah, so if we apply this is the Gaussian surface, right? So if we apply Gauss law, we have closed integral, surface integral E dot ds, and this is a Q enclosed by epsilon, right? Let's let's label something, right? So let's say this length is L, and this radius is R. Okay, so now let us calculate it. So this would be how much? E dot ds would be 3 integral, right? So this would be E dot ds 1 plus E dot ds 2 and plus E dot ds 3. And this is equal to Q enclosed by epsilon, right? So this Q enclosed is Q enclosed enclosed by this Gaussian surface. That we have to right. So
Yes,
we
sir.
know, and we know that for the first surface, the electric field is going in this direction. Right, electric field is going in this direction. This area vector direction is where? Where is the area vector direction?
Sir, on the right.
On the right. Okay, so this is the surface, right? If this is the surface, right? Let's say this is the surface. So for this surface, the area vector is normal. Area vector is always normal to the surface, right?
Yes, sir.
So this would be the area vector direction, right?
Hmm.
So, so the direction of the area vector for the first surface. So this would be this direction, right? For the first part.
Yes, sir.
So this is the area vector for one point. And this is electric field, they are perpendicular. So EDS would be what? This would be EDS cos 90,
Yes,
right?
sir.
Similarly, now this area chord vector has this area direction. So they are parallel, right?
Yes, sir. So
So this
0.
would be, yeah, so this is EDS. So this is EDS cos 0. Similarly, for the third case, what do we have? We have again, this one is this surface. So this surface is this direction,
It's a 90, sir.
right? So electric field is this, so this would be like so this is Q enclosed by epsilon, right? So then we know that this would be how much? This would be, this is cancelled, this is cancelled, and we can take this thing. So this is simply EDS, right? And
Sir,
Q
how
is
are they cancelled? 1 and 3?
1 and 3. So what is cos 90?
Sir, 1.
Cos 90 is 1 and cos 0.
No, sir, it's not 1. It's not 1.
Cos 90 is 0, right? Yeah, that is why this cos 90 is 0, so that is cancelled, right? Because this is 0. Cos 90 is 0. 0 multiplied by anything, that is 0. 0 multiplied by anything, that is why first and third are cancelled. Now we have taken our Gaussian surface in such a way that this electric field is uniform. So we can take this thing outside. And now I will not write this subscript. This is Q enclosed by epsilon, right? So what would be this is the small surface area. So if I integrate this surface area, then I'll get the whole surface area of the curved surface part, right? I will get the whole curved surface part. So what would be the curved surface area of this cylinder? What is the curved? Yes, what is the curved surface area of this cylinder?
The curved surface area of the Gaussian surface. Okay.
Pi RH, right? So that is the curved surface area of it, right? Remember it now. Curved surface area of the cylinder.
Yes, sir. No, sir, just have this right psychology test tomorrow and chemistry test tomorrow. Like,
Oh, so you have lots of tests happening. Yeah.
yes,
Yeah.
sir.
Yeah. So what we can do, such is life, right? Yes.
Yeah.
The test could be happening, right? So when you will go to your 11th or so you're already 12th time, so when you go to college life, then you'll have those. Again, those tests will not keep ready. What we can do? Maybe in future, but in future, we'll have some other. Okay, so yeah, so this is the total surface area of the cylinder. So that is 2 pi r, and height is L, right? Similarly, what is the charge enclosed? So we know that the this is a line wire, right? This is a line wire, so it will have what kind of distribution?
Linear distribution, sir.
Linear distribution, right? So let's say we are talking about this length. In this length, how much charge is enclosed in this length? Because we have taken this Gaussian surface. So in this length, how much charge is enclosed? So we know that linear charge density, that would be whatever charge is there at this point, Q, divided by this length L. So that is the Q enclosed, right? From here to here, whatever charge is enclosed, that charge divided by this length L, capital length L, so I have written capital L. So this would be the linear charge. So this Q enclosed would be how much? This would be lambda into L. Clear?
Yes, sir.
So this Q enclosed, this is capital, right? So this Q enclosed is lambda L divided by epsilon. So this L will cancel and we get the electric field as lambda by 2 pi r epsilon. How should I write it? I should write it. So 2 pi epsilon naught. So this is the electric field of a linear charge. So if whenever somebody asks that you have this infinite linear charge wire and you want to calculate the electric field at this point, so you can directly say that this would be, let's say this length is A. So this would be simply lambda by 2 pi epsilon naught A, and whatever this is the direction. So let's say this is x direction, so x for I hat, whatever we can write, right? So did you understand this part? Yes. Did you understand this part?
No, sir, can you just repeat it? I
Yeah. So
concentrate or
yeah.
something.
So yeah. So you see that we got for the linear charge distribution. This was the infinite linear charge wire or whatever this thing was. And now we have calculated the electric field due to this wire, right? So electric field due to this infinite linear charge wire at some distance, this point, this would be simply lambda by 2 pi epsilon naught and whatever this distance is, and direction would be in this direction, right? So whatever direction we are taking. Okay, is this thing clear?
Yes, sir.
Okay, so please note down this part and then we will talk about the other distribution. So we'll talk about the infinite Yeah, whenever you want me to scroll down, please.
Yes, sir. Just one more minute, sir.
Yeah.
Yes, sir. Done.
Then volume charge density would be, let's say you have this sphere, and in this sphere, this charge is, right? So this is a solid non-conducting. Yeah, whenever you want me to scroll down.
Yes, sir. Scroll down.
Yeah, whenever you want to scroll down.
Yes, sir, one moment. Yes, sir, scroll.
Yeah, whenever you have noted it down.
Yes, sir, just now. Yes, sir, done.
Okay, so the next thing that we'll do is yeah, one minute. Okay, so the next thing that we'll understand about is the yeah. So we'll talk about this infinite sheet. So we have two infinite sheets, or let's say we have one infinite sheet, and we want to calculate the electric field due to this infinite sheet. Right. So this has some distribution of charges. And what kind of distribution of charge would be there for this sheet? What kind of distribution would be there?
Sir, it's a uniform lateral distribution. It's a uniform horizontal
Surface,
distribution.
surface, right? So sheet is a
Sir.
surface. So there would be surface charge. So we'll talk about this distribution, surface charge density, right? Okay. So we have this sheet, and we will, for our purpose, we will take this kind of surface. So we will take a cylinder kind of, again cylinder kind of surface, right? Let me make a proper- We will take a cylindrical surface again. Okay. So again, how many surfaces are there? There are three surfaces. One,
Yes, sir.
two, and this third one, right? And this surface has a surface area direction in the this, right? For this finite sheet, the electric field would be in this direction, right? And in this direction, right? Is this clear?
Yes, sir.
So if we applying the Gauss, right? Applying the Gauss law, what we'll get? So let's say that this area is A, this area is also A, right? And we are not bothered about this area, right? So this area with which the charge would be placed, that would be also A, right? So then if we apply the Gauss law, let us write this Gauss law. So this is closed integral E dot ds, and this is Q enclosed by epsilon, right? This is the Gauss. So there are how many surfaces which are closing this sheet? There are three surfaces, one, two, and three. So if we write this thing as E dot ds, surface one, and then E dot ds, surface two, and then E dot ds, surface three. So this would be Q enclosed by epsilon, right? So first we wrote this closed integral. Now this closed integral has been changed to these three integrals, right? Open integrals. So these are making this closed integral, right? Okay, so for the one, first surface, the direction of area vector is in which direction? Yes, the direction of area vector is in this direction, right?
Yes, sir.
So that is parallel to electric field or normal to electric?
Sir, it is parallel to electric field.
Parallel to it. So angle is 0 degree, right?
Yes, sir.
So this would be E, and ds cos of 0 degree. This is one. For the second curved surface, oh, this is third one. So for the second one, we can also see that the area vector is perpendicular, parallel, right? Area vector is going in this direction. So this is again parallel. So we will write this as E. So E ds and cos of 0. What about this third one? What is the angle between the third one and the electric field? Yes. What is
Yes, sir.
what is the angle of the third surface with the electric field?
Third surface, sir, it will be 90 degree.
90, 90, absolutely correct. So this would be 90, right? So this is the third surface, and this is the EDS cos 90. So again, this part is cancelled, right? Okay, so now what we can do is that this is EDS, right? And this is EDS, and this is the Q enclosed by epsilon. So E is uniform, we can take it outside. This is DS plus E is uniform, we can take it outside. This is DS. And Q enclosed. So how much charge is enclosed, right? So we know that this area is A, and we know that surface charge density enclosing this charge would be Q enclosed divided by A. Correct, Arsalan?
Yes, sir.
So Q enclosed would be how much? That would be sigma A, right? So that much charge is enclosed through this loop, right? Okay, so and similarly, if we integrate the whole area, if we integrate this whole area, so that is again A. So this is EA plus EA, right? I will write it in here, sigma A by epsilon. So this is EA, and then sigma A by epsilon. The sigma A by epsilon naught. AA will cancel. So electric field would be sigma by 2 epsilon. So that is the electric field of a infinite sheet. Okay. So we have a sheet, and we will have the electric field of this sheet. In this side, if this is a positive sheet, so for positive sheet, the electric field would be coming outside. So in this side, electric field is sigma by 2 epsilon naught. And let's say this is some n hat direction, right? In this direction, we also have electric field, which is sigma by 2 epsilon naught and minus of n in this direction, right? So we have two sides of the finite sheet. In this side, we have a sigma by 2 epsilon naught. In left side, we have sigma by 2 epsilon. So this was about the finite sheet, right? But if we have this negative charge, so if this finite sheet contains the negative charge, then the electric field would be what? Incoming, right? That we already know from electric field lines, right? And
Yes, sir.
but magnitude would be same. This is sigma by 2 epsilon naught minus n hat, and this is sigma by 2 epsilon naught and n hat, right? N hat is right. So this was about the infinite sheet. I will talk about the combination in a moment, but you please, if you have any doubt, please ask me. Otherwise, we will go down. Okay, if you have any questions, please, this would be surface charge. Whenever you want me to scroll down, please. Whenever you want me to scroll down, please press like.
Yes, sir. Just give me one more minute, sir.
Yes, yes.
Yes, sir. Scroll. Yes, sir. Done.
Yeah. Okay. So yeah, this is very important to remember, and this will come when we do this capacitor. This will come in very handy, right? So let's say that you have placed kinds of parallel parallel infinite sheets, right? So let's say that you have placed. So we have these two parallel sheets, right? And let's say that we have two positive plates. So we know that for single plate, right? And let's say that this is y-axis, this is x-axis. So how many regions are there? Who is joining? Assalamu alaikum.
Walaikum Assalam, sir.
You are 1 hour late.
Sorry, sir. I was
Yeah,
outside. Last
yeah.
station.
Oh, you were out
Yeah.
of station. Yeah. So we just studied the application of this Gauss. So we talked about two kinds of distribution. One was this linear wire distribution. This blue thing is a linear charge distribution. And for that, we calculated the electric field, which was this. And then we had this sheet kind of thing. So for this infinite sheet, we calculated the electric field using the Gauss law. So these are the two things that we have done. Now we are trying to figure out that what would be the electric field due to two parallel sheets, right? And maybe they can be positive, they can be negative, they can be everything. So for negative, the electric field would be incoming. For positive, the electric field would be outgoing. Okay, so we have two kinds of, let me take that here. Okay, so we have two kinds of sheet, right? And both are parallel to each other. So this is in Y and Z plane. This is again in YZ plane. And this axis is X axis. We have this two sheets. Both are parallel to each other. And we know that how many regions would be there? How many regions would be there for these two sheets? How many regions? Yeah.
So you're asking me.
Yeah, I'm asking that how many regions would be there? If we have two parallel sheets, they are kept like this. So how many regions would be there? My face is between
Sir,
these sheets.
4 or 2?
So there would be three regions, right? One between the plates and then third. Is this thing here?
Oh, okay, sir. Reasons.
Yeah, three regions. Oh, so what did you? Not reasons. I was.
No, I didn't understand, sir.
Yes, I was asking about regions, right? So yeah, so there are three regions, right? So one is between the plates and the other twos are this left and this extreme right. So there are three regions of these plates. And there would be contribution from two plates, right? So one contribution would be from this plate. So for this one, in this region, the electric fields are going like this, right? And in this region, the electric field lines are going like this one. And in this region, the electric field lines for this one going away from it. Right. So all these are sigma by 2 epsilon naught. Right. And if I write the direction, so that is minus I hat. And this is again, let's say this is E1. Right. This is E2. And this is sigma by 2 epsilon naught minus I hat. And in this region, E3, due to this plate A. So let me write it as A. A, A, and A. And this is sigma by 2 epsilon naught, that is the magnitude, and direction is I hat, right? Positive I hat. So these are the electric field due to this A sheet. Now let us talk about this B sheet. For B sheet, in this region, the electric field would be away from it. Right? So E1B, that would be sigma by 2 epsilon naught minus I. Right? In this region, in the middle due to B1, that would be away from this sheet. So E2B, that would be sigma by 2 epsilon naught and I hat, right? And in here also, this would be away. So E3B is sigma by 2 epsilon naught ni. So which part is getting cancelled and which part is adding up? Which part is
Sir,
getting, yes,
sir, the region 2 is getting cancelled a lot.
yeah,
Because
yeah. So region
region 1
2,
and
yeah, these are in the same direction, so they are adding up, and in this side region, they are cancelling each other out. So we will have E2 net, that would be 0. We'll have E1 net, that would be sigma by epsilon naught, and I will write only the magnitude, right? So in this way we have, and in this E third region, we will have sigma by 2 epsilon naught again, but in the right hand direction. So these are the electric field due to two parallel sheets. Is this thing clear? Because we know that we have calculated what is the electric field due to this single sheet. And now we are combining these two sheets, right? So please note it down, and if you guys have any question, please tell. Combination of sheets.
yes, sir.
And this part will come in handy. So I will give you guys a question that what will happen if one is negative charge distributed and the other one is positive distributed. So then you guys, yeah, please check at your home what will happen to all these three regions. Yeah, I should zoom this thing out. Guys, please note it down. And then we will talk about the last one, which is the hollow sphere. So hollow sphere is the syllabus, and solid sphere is not. Yeah, whenever you guys have noted it down, please tell. Yes, noted everyone.
Yes, sir.
So now let us talk about another surface charge distribution. Why we are saying this surface charge distribution? So this one is this one is either solid conducting sphere, or we have hollow conducting or non-conducting sphere. So when I say solid sphere, which means that this sphere is filled, right? When I say hollow, so there's nothing inside, only the surface part is there. So for the conducting sphere, all the charges reside on the surface. So for a conducting sphere, all the charges reside on the sphere. And for the hollow one also, because there is nothing inside, so all the charges are residing on the surface. Right, so you have a tennis ball and then you have those furs of those tennis ball, right? So all those are on the surface. So all these charges are on the surface. So we will have surface charge distribution, not the volumetric distribution, right? So this is a solid one and this is a hollow, right? So we will calculate the electric field due to these kind of space. So let us calculate that. So we have a sphere and the charges are placed at the surface. Right? Let's say that total charge is Q. Total charge is Q. So due to this sphere, how many regions are there?
Sir, one.
One. Okay, so Arsalan is saying one. Mir, what about you? We have this sphere. We have uh, we have this sphere, right? If I make this sphere,
So
okay.
does the inside of the sphere count as a region or just the outside?
So
Because then there will
inside,
be two, right?
so inside is also the region, right?
Okay, sir. Then two.
So two regions. Yes. Now you are correct. Okay, Mir, is that clear? So we have two regions, one and two, right? We can talk about this surface also. So the surface would be the third region, but let us talk about one and two. Now, you guys see that if I want to, or if we want to calculate the electric field inside at this point, right? So let's say its radius is the radius of this sphere is r, right? And if I want to calculate the electric field at this point, this is inside, right? So there are two regions. One is inside and the other one is outside. So let us talk about the inside one. So for inside, we will make a Gaussian surface inside the sphere, right? So we will make a Gaussian surface like what kind of Gaussian surface we should choose? Will it be cylinder? Will it be cone? What kind of surface we should choose?
Uh, cylinder.
Cylinder.
The
Okay.
circle.
circle is not a sphere, right? Circle is,
Yes, sir. That's
so circle will not be a closed surface. We will take another sphere, right? We will take another sphere. So this would be the Gaussian surface. And that is another sphere, right? Which is enclosing this thing. So we have this Gaussian surface. And why we have chosen? Because we know that the electric field line would be normally passing through, right? So if we write the Gaussian Gauss law, so we have E dot ds, and this is the Q enclosed by epsilon naught. So do we have any charge inside this sphere? Do we have any charge?
yes, sir.
Any charge inside this surface, Gaussian surface?
Oh, no, sir.
So this is 0. So electric field would be 0, right? E inside that would be 0. Is this thing clear?
Yes, sir.
Okay, now let us talk about for outside. For outside, what we will do, we have this sphere, right? And we will take this radius is r, right? And we will take a Gaussian surface in this region, right? If you want to calculate outside this point, at this point we want to calculate the electric. So we'll take a Gaussian surface like this, right, outside of this sphere. So this is the Gaussian surface. And let's say its radius is r, right? So if we calculate, if we apply the Gaussian Gauss law, so we have E dot ds. This is Q enclosed by the charge in of Q, by epsilon, right? So we know that the electric field lines are going in this way, right? Electric field lines are going in this way, and the Gaussian surface is also in this way, right? So both have what degree angle? What is the angle?
Sir,
0 degree, right?
yes, sir.
So this would be simply E ds, right? Q enclosed by epsilon naught, and we know that electric field is uniform. So this we can take outside, and this is A ds only, the closed integral of this surface. So how much would be this integral? What is this surface area? What is this surface area? If radius is r, so what is this surface area of this sphere? What is the surface area of the sphere? Epsilon and beta. If you have a sphere, so what is the surface area of this sphere? We have
Fire square.
pi r square is the surface area of circle. I'm talking about a tennis ball. What is the surface area of the tennis ball? Or maybe a football, not a circle. Circle is pi r square, right?
Yes, sir. Yes,
So
sir. So,
this is 4 pi r square, right? How do you guys remember?
yes, sir.
So this would be 4 pi r square. And Q enclosed, how much charge is enclosed inside this surface? So that is Q, right? And this is epsilon. So electric field would be how much? That would be Q by 4 pi epsilon naught r square. So this is matching with the point charge. If you have a point charge and if you want to calculate the electric field at r distance, so electric field is how much? And let's say this charge is Q. So that is KQ by R square. So we are getting the same result, right? So the hollow sphere behaves like a point charge distribution. Is that thing clear? Is this thing clear, guys?
Yes, sir.
So if we draw the variation of the electric field with radius r, right? And let's say this is the surface of this sphere. And we know that inside the electric field is zero, right? Inside electric field is zero. And at the surface, it becomes kq by r square. So this is kq by r square. And then it varies as what? So it varies as 1 over r square. So it varies like, right? So this would be the variation of the electric. So the variation of electric field would be like this for a hollow sphere. Is this thing clear?
Yes, sir.
This is going like this, and then it is. Okay, so please, you guys note it down, and direction would be direction would be E vector, that would be Q by 457 r square r hat. So that would be the direction. Okay, you guys, please note it down, and if you guys have any doubts, please ask. So that would be the end of this chapter. Yeah, please note it down, and if you want me to scroll down, please tell. Yeah, whenever you guys want me to scroll down, please tell.
Yes, sir. Done.
Yeah. Okay, then please.
Yes, sir, done.
Yeah. Okay, what about you need noted? Yeah, so put down this part. Radiation of so radiation of electric field distance in a hollow sphere, right?
Okay, sir, done.
Yeah. Okay, yeah. So this is the end of this chapter, and you guys please start revising this chapter because this chapter is the most crucial. And from the next classes, I will talk about the electric potential. So I will rush in the next few classes and guys start. Okay.
Okay, sir. Assalamu alaikum, sir. Allah
Okay,
Hafiz.
so yeah. So but you have this class assessment after this, right?
Okay, sir.
So whenever you have whenever this class ends, we will take it. Okay. Okay. So all the best, Arsalan. You have this psychology test. Right? So can you read minds, Arsalan?
Huh? Yes, sir.
Can you read minds?
No, sir. No. Just predicting behavior, sir.
So, oh, just predictive. Yeah. Okay, so some patterns you can figure out, right?
Yes, sir.
Okay, yeah. So see you guys on yeah. So I will see you guys tomorrow, and yeah. So all the best, Salam, and yeah. Allah Hafiz, me, Allah Hafiz, Salam. See you
Allah
guys.
Hafiz, sir.
Allah Hafiz, guys.